Have you ever been stuck in the middle of a polynomial division problem and it's just a total mess? You're not alone. But what if I told you there's an incredibly slick, super fast shortcut? One that not only gets you the answer, but actually shows you what the equation is really made of? Well, let's get into it.
So just look at this. On the left, you've got your classic polynomial long division. It's kind of sprawling, a little tedious, and honestly, there are a million places to make one tiny mistake. But on the right, that's where we're headed. It's clean, it's compact, and it is seriously powerful. Let's see how we make that happen.
All right, here's our game plan. We're going to start with the problem, the long way around. Then we'll introduce the faster path. We'll cover the all-important rules of the road, uncover its real purpose, which is finding factors, and then take a quick peek at where this all leads beyond the basics.
You know, to really appreciate a great shortcut, you've got to understand the long road it helps you avoid. And in the world of polynomials, that long road is definitely long division.
And it's so true, right? With all those variables and exponents and subtraction steps, it's just way too easy for one little minus sign to go wrong and throw the whole thing off. If you've ever gotten frustrated with it, trust me, you are not alone. But we are about to fix that problem for good.
So, let's trade in that long, winding road for a high-speed expressway. It is time to meet the star of our show today, synthetic division.
The real beauty of this method is just how simple it is. It completely strips away all the extra stuff, the x's, their powers, and it lets us focus on what's really doing the work, the numbers, the coefficients. It's just a much more streamlined and efficient way to get things done.
The entire thing really just boils down to a simple, repeatable rhythm. Bring down, multiply, and add. Bring down, multiply, and add. Seriously, that's it. That is the engine that drives this entire technique.
Let's walk through one together. We're dividing x squared plus 5x plus 1 by x plus 3. So first we set it up. We just use the coefficients, 1, 5, and 1. Now the number we're dividing by comes from the root of our divisor, basically what makes x plus 3 equal to 0. Well, that's negative 3. Okay, now for the rhythm. Bring down that first number, the 1. Then we multiply diagonally. 1 times negative 3 is negative 3. Now we add vertically. 5 plus negative 3 is 2. And we just do it again. Multiply the 2 by negative 3, you get negative 6. Add 1 and negative 6, and you get negative 5. And that bottom row, that's our answer. The last number, negative 5, that's the remainder. The other numbers, 1 and 2, are the coefficients for our quotient. So our answer is 1x plus 2. Simple.
Now, like any powerful tool, this one comes with a couple of ground rules. We want to make sure we're using it right and, not falling into any of the common traps.
So, there are two main things to keep in mind for the standard method. First, the thing you're dividing by has to be a simple linear factor, something like x minus 2 or x plus 5. Second, the coefficient on that x has to be 1. But don't worry, there's a really neat little workaround for when it's not, and we're going to get to that in just a second. But first, let's tackle a question that trips up a lot of people. What do you do when your polynomial skips a beat? Like it goes straight from an x cubed term down to an x term, with no x squared in sight. And the answer is simple, but it is absolutely critical. You have to use a 0 as a placeholder. So for this example, x cubed minus 125, we can't just use the coefficients 1 and negative 125. We have to account for the missing x squared and x terms. So we pop in zeros in their spots. Forgetting this step, that will guarantee a wrong answer every single time.
Okay, remember that messy problem I mentioned? What happens when our divisor looks something like, say, 3x plus 1, where that leading coefficient isn't a 1? Well, our standard process just needs a tiny little adjustment.
And here is the trick. It's so cool. You still do synthetic division just like normal, using the root of the divisor. But when you get your result, there's one extra step at the very end. You take all the numbers in the quotient part of your answer, so everything except the remainder, and you divide all of them by that leading coefficient, a. It's a super simple tweak that makes this method work even for those trickier problems.
So look, we know synthetic division is a fast way to divide. But that's not its real job. Now we get to the aha moment. The real power of this whole thing is in factoring polynomials. And this is all thanks to a beautiful little rule called the factor theorem. And it's so elegant. It basically says that if you do a division and you end up with a remainder of 0, then the thing you divided by, that x minus c, is a perfect factor of the original polynomial. It fits perfectly.
Let's see this thing in action. Take a look at this example where we're dividing by x minus 5. We run through the whole synthetic division process, and what's that last number in the result? It's a 0. A 0 remainder is the magic signal. It proves without a doubt that x minus 5 is a factor of that original polynomial.
Now let's go back to our very first example to see the other side of the coin. Remember, the remainder there was negative 5. Because it's not 0, the factor theorem tells us, just as definitively, that x plus 3 is not a factor of that polynomial. It just doesn't divide in cleanly.
So here's the big takeaway. Synthetic division isn't just a calculator trick. It's a powerful diagnostic tool. It lets you rapidly test different values to see if they're roots. And by doing that, it helps you find the factors, the literal building blocks of any polynomial.
And this isn't just some trick you'll use for algebra homework and then forget about. This hack is actually a fundamental concept that pops up in some pretty advanced areas of math and computer science.
The same core logic works when you start dealing with complex and imaginary numbers. In linear algebra, it's actually a key part of solving certain kinds of matrix problems. And in computer science, this whole principle of breaking things down efficiently is used to build faster algorithms for pretty much everything from graphics to data analysis. I think this quote just sums it up perfectly. The genius of this method is that it flips the operations around. It cleverly trades harder operations for easier ones. It replaces tricky division with simple multiplication, and it replaces all that careful subtraction with straightforward addition, making the whole thing faster and way less likely to have errors.
So, as we wrap this up, I'll leave you with this thought. Is synthetic division just a neat little shortcut to get out of doing long division? Or is it something more? Maybe a key that actually unlocks the secrets of polynomials and lets us see how they're built from the inside out. It's a tool that starts simple, but man, it opens the door to some really deep stuff.